Chapter 19b, Nucleophilic addition of aldehydes and ketones. In this section, we focus on negative charged nucleophiles. In the carbonyl compounds, both carbon and oxygen are sp2 hybridized, so each of them has an unhybridized p orbital perpendicular to the molecular plane, and these p orbitals overlap forms the pi bond. Carbon, oxygen, hydrogen, they are all in the same plane. So it's a planar structure, and the angle close to 120. CO double bond distance is about 122 pm. The carbon-oxygen bond is polar due to the different electronegativity. We can draw a resonance structure to show carbon has a positive charge, oxygen has a negative charge. And the consequence is the negative oxygen attack positive hydrogen or aluminum, which has empty p orbitals. Oxygen serves as a base. On the other hand, the positive charged carbon may be under attack by nucleophiles. Nucleophiles means the group or atoms that loves nucleus, and these are usually electron-rich atoms or groups. Here shows the general mechanism of nucleophilic addition reactions. A nucleophile, which has a lone pair electron, attack positive charged carbon, forms a bond. The carbon-oxygen bond break, 2 electrons goes to the oxygen, forms a coxide anion. This anion is protonated, forms alcohol. So a carbonyl carbon can be attacked by a nucleophile. Here are some nucleophiles. These are negative charged nucleophiles: hydroxide, hydride. Carbanion comes from Grignard reagent, a coxide, cyanide, and these are very strong nucleophiles. Here are some neutral nucleophiles: water, alcohols, amines. They all have lone pair electron, and they are nucleophiles, but they don't have negative charge, so they are weaker than the negative charged nucleophiles. In general, aldehydes are more reactive than ketones. There are 2 reasons. Sterically, a ketone is more crowded than an aldehyde. This is because in aldehyde, there's at least one side of the carbonyl group is hydrogen. And therefore, this carbon, the carbonyl carbon, is more exposed to be attacked by a nucleophile. On the other hand, in a ketone, both sides are carbon. And so they can connect to hydrogen, and the carbonyl carbon is crowded and shielded from the attack and less reactive. Electronically, an alkyl group is an electron donating group. In aldehyde, there's only one alkyl group that donates electron to this positive charged carbocation, but in ketone there are 2 of them, make this carbon less electron positive. And if the carbon is less electron positive, it's not as reactive under attack by the nucleophiles. Among aldehydes, benzoaldehyde is less reactive than other aldehydes. And this is because benzene is electron donating. We can draw 4 resonance structures here to show that the partially positive charge on carbon is delocalized to the benzene ring. And this makes the carbonyl carbon less positive and therefore less reactive towards nucleophiles. The general mechanism involving negative charged nucleophile includes 2 steps. Step 1 is nucleophilic addition. A nucleophile, which is one of the negative charged ion, attacks positive charged carbon. Note that both carbon and oxygen are sp2 hybridized. The molecule is planar. Both carbon and oxygen has a p orbital that is perpendicular to the plane. Nucleophile attack from above the plane. The product is a alkoxide ion. Carbon change from sp2 to sp3 hybridization. The ion is tetrahedron geometry. Angles are around 109 degrees. In the second step, the alkoxide is protonated by hydrogen ion to form an alcohol. Here again shows the two-step mechanism. Nucleophilic addition, protonation give you an alcohol with nucleophile added to the product. You have already seen some of these reactions. For example, the reduction with sodium boron hydride followed by protonation give you an alcohol. Grignard reaction followed by protonation give you an alcohol with carbanion added to the product. And there are some new reactions we're going to see. Cyanide reaction give you cyanohydrin, and an ylate reaction with carbonyl compound give you alkene. Let's go over the two most commonly used reducing reagents, sodium boron hydride, lithium aluminum hydride. Both are hydride source. Sodium boron hydride is made by combining hydride with boron. Although boron hydride provide hydride, they are not exactly the same. Hydride is a base that react with positive charged proton. They form hydrogen gas. Boron hydride, since it has a larger size than hydride itself, it likes to react with positive charged carbon, and therefore it's a nucleophile. Similarly, lithium aluminum hydride, the aluminum hydride has even larger size, and so it likes carbon cation more than boron hydride, and therefore it's a better nucleophile or stronger nucleophile. Both sodium boron hydride, lithium aluminum hydride can be used to reduce aldehyde and ketones into alcohols. In aldehyde, since at least one side of a carbonyl group is hydrogen, adding another hydrogen gives you a primary alcohol. In ketones, since both sides are alkyl groups, adding a hydrogen to the carbonyl carbon gives you a secondary alcohol. The hydride reduction reaction follows two-step mechanism as we shown before. You may still remember drawing the mechanism when we discussed the synthesis of alcohols. Now let's go over this mechanism for this particular reaction. So first draw the aldehyde, and then draw a hydride comes from sodium boron hydride. And nucleophilic addition, attack the carbonyl carbon, pi bond break goes to oxygen, forms a alkoxide. All right, and the second step, alkoxide protonation. All right, and so arrow shows electron forms a bond between oxygen and hydrogen. Another arrow shows the bond break to form a water, and the product is alcohol. Practice. What carbonyl compounds would you reduce to obtain the following alcohol? You may still remember that we did this exercise before when we study the synthesis of alcohols. And from carbonyl compounds, and this hydrogen must come from hydride attack, and this hydrogen come from protonation. And so the reactants must be this compound with a CO double bond, and that's a ketone. For ketone, both sodium boron hydride, lithium aluminum hydride work. So it follows two-step mechanism. One is a reducing reagent, sodium boron hydride, and second is hydrogen ion protonation. Grignard reactions also follow two-step mechanism to form an alcohol. Grignard reagent can be made by mixing alkyl halides with magnesium metal. The result of the Grignard reaction has two effects. One is to convert carbonyl group into alcohol, and the second forms a carbon-carbon bond. Here shows an example of Grignard reaction to convert butanol into 3-hexanol. You learned how to draw mechanism when we studied the alcohol synthesis. So here let's go over this again. So draw the butanol molecule and carbanion from Grignard reagent, nucleophilic addition, pi bond goes to oxygen. The intermediate is a carboxide ion, but with a carbon-carbon bond formation. Next step, protonation. Give you the final product. Here is a comparison of hydride reduction and Grignard reaction. Both follow two-step mechanism, nucleophilic addition, protonation. In hydride reduction is the hydride attack. In Grignard reagent is a carbanion from Grignard reagent. And the carboxide intermediate, one is hydrogen added, one is carbanion or alkyl group added. And the second step is protonation. Both give you alcohols. Grignard reaction give you a larger alcohol due to the added alkyl group. Here are some examples of Grignard reactions. When synthesized Grignard reagent, the reactant molecule cannot have a functional group that can interfere with Grignard reagent, and that includes hydroxy group, amines, thiols, carboxylic acid groups. Also, carbonyl compounds, cyanide, nitrile groups. Here's a sample question that you already saw before, and let's just go over very briefly. We want to make alcohol from carbonyl compounds by Grignard reaction. So any of this group may come from the Grignard reagent. And so there are 3 ways. Okay, so ethyl can come from Grignard attack, all right, or methyl from Grignard, or even benzene. Cyanide is a strong nucleophile that can also attack carbonyl compounds. The reaction follows two-step mechanism. First step, nucleophilic addition forms a carboxide, which is protonated in the second step. In this case, we can use hydrogen cyanide as the protonation source. And the product is alcohol with a cyanyl group and called cyanohydrine. One of the very useful reactions ketones aldehydes undergo is called Wittig reaction. In this reaction, a carbonyl group is converted to CC double bond alkene by an ylide. As we know, phosphorus and nitrogen are both group 3 atoms, and they have 3 valence electrons. They form 3 bonds with a lone pair electron. If the substituents are benzene ring, this is called triphenylphosphine. Triphenylphosphine can react with alkyl halides followed by deprotonation, gives you a compound that can have 2 charges on adjacent atom, positive on phosphorus, negative charge on carbon, and this is called triphenylphosphorus ylide. When carbonyl, ketone, or aldehyde react with triphenylphosphorus ylide, this alkyl group will replace the oxygen, forms the carbon-carbon double bond. And this is a very useful reaction because it forms a CC double bond with predictable structure. Here shows the mechanism of Wittig reaction. Since the carbon in the ylide has a negative charge, it undergoes nucleophilic addition to attack positive charged carbon, forms carbon-carbon bond. At the same time, the pi bond between carbon-oxygen move to oxygen, forms a carboxide intermediate. In this intermediate, oxygen has a negative charge, phosphorus has a positive charge, and they combine forms a 4-member ring intermediate. And this intermediate undergo rearrangement. The 2 electrons between carbon-oxygen move to the oxygen-phosphorus, form a double bond. At the same time, the 2 electrons between carbon-phosphorus move to carbon-carbon, forms a pi bond. So a double bond, carbon-carbon double bond is formed. So the net effect is that when a carbonyl compound reacts with a phosphorus triphenyl phosphorus ylide, oxygen triphenyl phosphorus combined together forms a byproduct, and the carbon-carbon forms a double bond. The 2 substituents are untouched on the structure. Here shows how triphenyl phosphorus ylide is synthesized. We start with triphenyl phosphine, which has a lone pair electron, and it's a nucleophile. It will react with a primary alkyl halide, undergo SN2 reaction. The lone pair electron attack the methyl group here, leaving group leave gives you a phosphonium bromide. Note the phosphorus has a positive charge. Next step, we add a strong base, and usually is butylidene. Remember, it's like a Grignard reagent, so very strong base. It will deprotonate one of these hydrogen and give you a carbon with a lone pair electron and a negative charge. So positive charge on phosphorus, negative charge on carbon. It's a ylide. Okay. Now the phenyl group we can simplify as pH, and therefore this molecule can be written as phosphorus pH 3. So triphenyl phosphorus ylide. So CH2 is this one with a negative charge. Now the carbon has a lone pair electron, and we can also draw resonance structure. So this can go here, and the resonance structure can be written as a double bond between carbon phosphorus and the triphenyl. So this is another way to draw the phosphorus triphenyl phosphorus ylide. Okay, either a double bond between carbon phosphorus or positive charge on phosphorus, negative charge on carbon. Now note that since this reaction is SN2 reaction, so the alkyl group usually is a primary. So the product, the ylide, is usually typically a primary ylide. Here shows an application of Wittig reaction. Suppose we want to make a double bond, carbon-carbon double bond. We start with this molecule, and we want to make here CH2 and this molecule a CC double bond. One way to do it is to follow 2-step reaction. One is add a Grignard reagent. So this carbanion will attack carbonyl carbon, and it will give you an alcohol, CH3OH. And then second step, we add phosphorus oxyylide, the chloride. And remember, phosphorus oxychloride is a dehydration reagent. It will remove water from this molecule, forms a double bond. So hydroxy is removed, hydrogen, so maybe this hydrogen forms a double bond here, or one of these hydrogen forms a double bond here. So what we get is a mixture. In fact, this is only 10%. Okay, this is 90% because this is more branched one. Okay, and that's not good because this is our desired product. Another way to do it is the Wittig reaction we just learned. So triphenyl phosphorus ylide. Okay, so carbanion here only 1 carbon. So after you add this Wittig reagent, and the net effect is this oxygen combined with phosphorus, triphenyl phosphorus becomes a byproduct, and this carbon combined with this carbanion forms the desired product. So compare these two methods. One gives you only 10%, one gives you the only product. Here shows the key step in industry to synthesize vitamin A. In this step, two small molecules combine forms a larger molecule. Sodium methoxide is a strong base that can deprotonate one of these hydrogen, forms a negative charged carbon, and that becomes a triphenylphosphorus ylide. The triphenylphosphorus part combines with oxygen together. At the same time, the carbanium part combines with this carbonyl carbon, forms the double bond here. Practice. What carbonyl compound and what phosphorus ylide might you use to prepare 3-ethyl-3-pentene? So first draw the structure of the product, and as you can see, this double bond can be synthesized by combining a carbonyl compound CO double bond with a triphenylphosphorus ylide. And because triphenylphosphorus ylide is synthesized by SN2 reaction, so the ylide must be primary. So in this structure, the right side, the smaller part, must come from the ylide part, and the left side comes from the ketone part. And therefore, here is the ketone, and because the right side has 2 carbon, so the ylide carbanium also have 2 carbon. And when you combine these two molecules, oxygen combined with triphenylphosphine, and the carbanium goes to here, forms a double bond, and that gives you the desired product. In summary, ketones aldehydes react with negative charge nucleophile, undergo two-step mechanism. First step is nucleophilic addition, forms a coxide, and the second step, protonation, gives you an alcohol. We went over two familiar reactions. One is reduction by sodium boron hydride, one is reaction with green other reagent. Both give you alcohols. A new reaction is the ketone aldehyde react with cyanide and give you the cyanohydrine. A very useful reaction is called Wittig reaction. In this reaction, ketone aldehyde react with triphenylphosphorus ylide, and the triphenylphosphorus combined with oxygen, and the carbanium combined with carbonyl carbon forms a CC double bond. These are the homework problems.